All right, so in today's lesson, take two, I just finished 30 minutes of this lesson and it cut out and I have to restart. So in this lesson, we are going to be looking at one-dimensional momentum conservation. For the purposes of remote learning, we're only going to be limiting ourselves to one-dimensional conservation of momentum. If you want to learn about two-dimensional conservation of momentum, I will be putting an optional learning module up on my website on Friday. Again, that is optional, okay? I will only be assessing you on the one-dimensional conservation of momentum. So the bottom line is this: momentum is conserved in a collision. Scientists explored this. Okay, so Newton kind of laid this down in words, okay, that the total momentum, so whether it's one or two or three or four objects, the total momentum of a closed, isolated system does not change. So what do we call a system? A system is a group of objects that are involved in a collision. Okay, so there can be any number of objects. It's considered closed if objects don't come in or out, so they don't leave or enter, and it's considered isolated if there's no external force acting on it, no net external force, which means essentially no friction. So our systems are going to be frictionless, okay, and they're going to be closed and isolated, and therefore momentum will be conserved. So the law of conservation of momentum, that's essentially what we're learning about today. It's useful for analyzing the collision of objects. There's three types of collisions, which we'll get to in a second. But in a more useful form, what does the law state? The law states this, that the total momentum of a system before a collision equals the total momentum of a system after the collision. And so again, if we had more than one object that's moving or in the system, we would have to add up the individual momenta to get the total and then do the same thing for afterwards. So if there's zero momentum before, then there's going to be zero momentum after. If the momentum total is 10 kilogram meters per second before, it'll be 10 kilogram meters per second after. There's three types of collisions that we will look at. First, elastic. Second, inelastic. And third, recoil. All right, so elastic collisions. Elastic collisions basically means that when the objects collide, they move apart separately. They don't stick together. So we'll look at our first example for learning. So we're talking about a glider, okay? So it's like a little object that rests on an air track, which is frictionless. So there's two gliders, glider A and glider B. They're both moving, so they both have an initial velocity, and they collide. After they collide, glider A has a velocity, and we want to find the velocity of glider B after the collision. So we want to find V to B. That is our unknown. We are going to use the law of conservation of momentum to solve this. So we start with stating the law. So P total 1, which I'll say 1 is before, equals P total 2, which is after. Now there's two objects, A and B. So P1A plus P1B must equal P2A plus P2B. Again, 1 is before, 2 is after. Because we don't know the momenta, we will have to expand this out. And so we know that P equals mv from yesterday. So we would say that ma for glider A times v1a, so that's m times v1a, that's the momentum of glider A initially, plus mv v1b must equal ma v2a plus mb v2b. So we're just expanding out the definition of momentum. So we just essentially plug and chug at this point, all right? So if we have two objects in an elastic collision, basically this would be kind of your go-to equation, because I'll underline what our unknown is. Our unknown is the final velocity of the the final velocity of the glider B. We know ma, we know nb, we know the initial v of A, the initial v of B, and we know the final v of A. So we're just essentially solving for the final velocity of B. So we can plug and chug. So MA is 0.355 kilograms. So 0.355 kgs times VA, which was 0.095 meters per second. 0.095 meters per second. That's MAV1A plus B. So mass of B is 0.71 kilograms, 0.71 kgs times B1D, which is 0.045 meters per second, 0.045 meters per second. That's going to equal MA, which doesn't change, 0.355 kilograms times V2A, which is 1.35 meters per second, plus MB, which doesn't change, 0.71 kgs times V2B. Now this looks very busy and might be very scary, but it shouldn't be too bad because we can clean up the left-hand side, okay? M times V, add them together. Then we will take M times V and subtract that over, and then we divide by the mass. So it really shouldn't be too busy. So we'll clean up the left side, okay, to get the total momentum before. So the total momentum before will equal this, 0.355 times 0.095, and then we'll add 0.71 times 0.045, and we get 0.065675. 0.065675 kilogram meters per second equals, we'll figure out that number, which is 0.355 times 1.35, 0.47925, 47925 kilogram meters per second plus 0.71 times V2B. So we have to subtract the 0.47925 to the left side. So we'll do that. So we'll take 0.065675 and we'll subtract 0.47925. And we're going to get a negative number. That's okay, it just means direction. So negative 0.413575, negative 0.413575 kilogram meters per second equals 0.71 times V2B. And now we can divide that out. So V2B then would equal the 0.413575 divided by 0.71 kilograms, and we get negative 0.5825. So negative 0.5825 meters per second. And so the sig figs, I believe we're talking 3 sig figs. Nope, sorry, we're talking 2 sig figs. So the final velocity of B after being hit by glider A, 2 sig figs, V2B would equal negative 0.58 meters per second. And that is how we do the law of conservation of momentum for a one-dimensional collision between two objects that's elastic. Again, we start with the conservation of momentum statement. The total momentum before equals the total momentum after. We divide it up into the fact there's 2 moving objects, okay? And then we break it down into MV because that's the definition of momentum. So the one that I boxed here would be kind of your formula for 1D collisions. All right, the second option are inelastic collisions. So inelastic collisions would be two objects that collide and stick together. And that would be kind of like train cars sticking together or football players colliding with each other. So if they stick together, that means M total would equal M1 plus M2 and so on. So that's kind of what we have to deal with in inelastic situations. So we have a railroad car traveling, it strikes an identical car. So we'll call the first car A and the second car B. It's at rest, so V equals 0. If the cars lock together, what's their common speed afterwards, which means V2. So again, we are going to have P1 total equals P2 total, conservation of momentum. Now we have two objects before, so we have P1A plus P1B will equal P2. Now we say only P2 because after they stick together, they're only one moving object. So this is for inelastic. Okay, so P1A would be MA times V1A plus P1B. Now, the identical car B is at rest, so it must have a 0 momentum. And that would equal M total times V2. They're identical cars, so they both have a mass of 10,000 kilograms. So 10,000 kilograms times 24 meters per second plus 0 must equal M total, which would be 10,000 plus 10,000 or 20,000 times V2. So 10,000 times 24, you get 240,000. Would equal 20,000 times V2. So divide by 20,000 and you get 12. So V2 then would equal 12 meters per second. So the common speed of both cars afterwards, V2, would be positive 12 meters per second. So inelastic's a bit quicker because the objects stick together. Again, we start with total momentum before equals total momentum after, split it up, P1A, P1B. Afterwards, they stick together, so there's only a final momentum, V2. The second car isn't moving, so that has a momentum of 0, and we go ahead and we solve for V2. Recoil. Recoil is when two objects that are initially stuck together separate. So we have A and B before, and they separate afterwards. And what will happen is that they will move in opposite directions. And that's called recoil. Okay. Calculate the recoil velocity of a 4-kilogram rifle, which we'll call mass 1, after it shoots a 0.05 kilogram bullet, M2, at a speed of 280 meters per second. Okay, so again, we begin with P1 total equals P2 total. And actually, we'll call the rifle A, and we'll call the bullet B. Sorry about that. I'm going to confuse you with the 1 and 2, because the 1 is initial and the 2 is final. Okay, so we have two objects, the rifle and the bullet. So the bullet is A is the rifle, B is the bullet. Okay, so we will have P1A plus P1B equals P2A plus P2B. Alrighty, so the bullet, we are going to say initially V1B is going to be 0 in the rifle. So therefore the bullet's momentum is 0. So this would be MA V1A for the rifle. Back up. The rifle and the bullet are both at rest. So they're both 0. My apologies. So the initial momentum is 0 because the rifle is at rest. V1A is also 0. There's nothing to say that it's moving. So the initial momentum is 0. So that must equal the final momentum of A, so that would be MA V2A plus MB, the bullet, times V2B. Now we want to find the recoil velocity of the rifle. So 0 for the initial momentum must equal the rifle. So that's 4 kilograms times V2A plus the bullet, 0.050 kilograms times 280 meters per second. So we're simply going to multiply these two together, subtract it over. It's going to be negative, which makes sense because if you've got the rifle and you've got the bullet's going to go forward and the rifle's going to move backwards. It's a terrible rifle, but I think you get the idea. Okay, so we'll multiply this out, 280 times 0.05, 14. So 0 equals 4 V2A plus 14 kilograms meters per second. Subtract that over. So negative 14 equals 4 times V2A. So we simply take the negative 14 and we divide that by 4 kilograms, negative 3.5. So V2A is negative 3.5 meters per second. And that would be the recoil velocity of the rifle. And that is how we explore or solve one-dimensional recoil problems involving conservation of momentum. The rifle moves so much slower because its mass is way larger than the bullet. But that is still significant. And if anybody's ever shot a rifle, you'll notice that it does push back into your shoulder. And that's because of the law of conservation of momentum. So those are our 3 examples. What's left here for you are some practice problems, so you can work on that tomorrow. And I hope that this makes sense. You can read through conservation of momentum in your textbook. Again, we are focusing on one-dimensional for this remote learning. There will be optional 2-dimensional learning on Friday. Good luck.